is also recorded, and I think it will be put to YouTube. However, there will be yet another recording as it happened for most of the lectures of the first term. So today is the first day of the second term. I hope that you already attended the first lecture of Numerics 1. It was online. However, for this course, as soon as COVID team will allow us to meet in person, those of you who stay in the ICTP campus hopefully will join me in this lecture room for the in-person lectures. Okay, now I'm talking about structure of the course. The course consists of 4 chapters. And remember, we are dealing with the many-body physics. I will come back to more precise definition of what we are going to discuss. So these 4 big chapters, and now I start with the blackboard. So it is lecture number 1. Let me see how it looks like. Can you see it? I see from my laptop that the blackboard has proper frontal projection, so there are no distortions. And is my script visible, or I need to write it in the bigger letters? Sorry, I need your feedback, therefore I will ask questions all the time. So if someone like Joab unmute his microphone and tell me on behalf of everybody if you can see what I'm writing and if you can understand what I'm saying, if the sound is good, please let me know. Otherwise, I will be teaching you for 1 hour and a half, and if you listen nothing, if you see nothing, if you understand nothing, what then the reason of doing these lectures? So, do you see my script on the blackboard?
Yes.
Okay, so today is lecture number 1, and the title of this lecture is Symmetries. Sorry, please say it again.
Yeah.
Okay, so, but before coming to the topic of this course, I would like first to discuss the structure of this course, the goals and objectives of this course, then the structure of and more a timetable of events we are going to have during this course. And the course is going to be interactive, as I said. We do plan several tutorials, and we will readjust the number of tutorials to the actual needs. So, as I said, the course will consist of 4 chapters. Big chapter. So, chapter 1 is fermions. Chapter 2 is bosons. Chapter 3 is superconductivity. And chapter 4 is magnetism. Can you see it?
Yes, I can.
Good. So, what is going to be inside the chapters? How the chapters are structured by themselves. So, for fermions, we start with the ideal Fermi gas. So, now, chapter 1. Ideal Fermi gas, Fermi liquid, which means fermions with interaction. We will quantify and discuss this interaction. Then we discuss effects of Coulomb interaction. And in this lecture, I will introduce to random phase approximation. We calculate the electric constant as a function of the momentum and the frequency. We discuss the properties of this dielectric function and actually discuss how the Coulomb screening works and plasmons in the metals. All this about is the theory of metals, and we also discuss magnetism of itinerant fermions. Namely, Pauli paramagnetism, Landau diamagnetism, and also Stoner magnetism. So this is basically what is going to be discussed in the first chapter. However, you see that the course is going to be cross-linked. And of course, we will come back to discussion of fermionic excitations in the chapter of superconductivity. And we will also discuss strongly correlated systems in the chapter of magnetism. I'm going to come back to this point later. In the Coulomb interaction, we will also touch upon a Friedel oscillation when you have a charged impurity in the metal. But all chapter about fermions is actually has a goal to introduce you to the theory of metals. It's going to be complementary to what we discuss in the course of electrons and phonons in solid. As you see, mostly I will discuss it from the point of view of thermodynamics. So, in the chapter number 2, bosons, we adopt the very same spirit. Namely, we start with the ideal Bose gas. Then we come to discussion of interacting. Namely, weakly interacting. We will quantify what does it mean that interactions are weak or strong. Then we discuss Bose-Einstein condensation. We discuss superfluidity. And we discuss behavior of bosons in so-called ultra-cold atomic gases. So here, as I said, all this under umbrella of theory of metals. So, in the chapter number 3,
Professor?
yes?
Sorry to cut you, but somehow I hear some kind of speaker background noise.
This I cannot help, I'm sorry. I think this is not speakers, this is ventilating system, because I also hear this noise, but the room is ventilated, so it's just fan which works. I'm sorry.
Yeah, and also sometimes I cannot hear every detail what we speak clearly. So,
Okay, when I speak being faced to the screen, is it better? If I speak now, do you hear me? Because look, for me it's first experience with this room. I used to give a lecture in a different room with a bigger blackboard, but you understand that I'm going to write down something on the blackboard and at the same time speak. But as soon as you experience some problem with listening to me or whatever, just tell me. Okay? I will try to speak slower, not very fast, and if necessary, I will repeat things. Okay? Okay, now superconductivity. So, we start with the phenomenology of superconductors. Which means the theories which precede the microscopic theories and discuss some experiments which create a puzzle in order then to discuss how this puzzle is going to be resolved. This phenomenology contains London equation, thermodynamic and electrodynamic of superconductors, but then we will start with the most powerful phenomenological theory of the superconductivity, which is Ginzburg-Landau's theory. And then, in terms of Ginzburg-Landau theory, we discuss vortices. Then we start discussing microscopic theory of superconductivity, which is Bardeen-Cooper-Schricker theory. And we discuss Josephson. Again, you see that I put like 4 times bullets, and it more or less represents one bullet is one lecture. However, we can discuss at some point that if we would like to discuss, for example, quantum Hall effect, or we would like to put more emphasis on experiments, it's also very useful. So we have a freedom to add some more items here. I put 4 big chapters, but at some moment we need to insert a crash course of theory of phase transitions. Did you discuss phase transition in the course of statistical mechanics?
Yes, we looked at the argument.
Did you discuss Landau theory of phase transition?
no, they haven't reached that part.
So do you know what is lambda phi to the 4 theory? Because before discussing this cooperative phenomena like superconductivity and magnetism, and all this is about phase transitions, namely second order phase transition, we already meet phase transition in the discussion of Bose-Einstein condensation. I need to introduce you to the basic of the phase transition theory, namely at least Landau theory before I come to Ginzburg-Landau theory. So this phase transition, let me put it somewhere here. So I need at least to have Landau up and down fluctuations. And if time permits scaling. So, do you have anything from this in your previous courses? I think that something is going to be discussed in advanced statistical mechanics, but advanced statistical mechanics will start when I will already finish my course. Therefore, unavoidably, in order to be able to discuss the cooperative phenomenon, which is in the centrum of everything I'm going to present in this course, I will need these phase transitions. So, then I will devote at least 2 or maybe 3 lectures to the phase transition theory in order to introduce you to what I need for the course of superconductivity and magnetism. And then, oh, it's terrible. If it's going to be like that. So, last but not least is magnetism. And as you see, we already have something about magnetism of free electrons and weakly interacting electrons, namely paramagnetism and diamagnetism, is not at all related to the effect of interaction. It is rather related to the spin and orbital degrees of freedom of the electrons. The stoner magnetism will then assume that electrons interact with some interaction. So the magnetism will start and mostly devoted to the theory of local magnetism. So this magnetism of solid states, solids, will be mostly related to local degrees of freedom. For example, if you have an atom and you have a deep shell partially filled, then you have spin or total momentum associated with atoms forming a lattice, and therefore we discuss this local effect of local magnetism. In particular, we will discuss ferromagnetism and antiferromagnetism. Then, so when I say magnetism, it's almost everywhere local. Then we discuss spin dynamics. And we discuss effects of strong electron-electron correlation. In particular, we will discuss effects of strong electron-electron correlation in the chapter of superconductivity. And this is high temperature superconductivity. And here we are going to discuss strongly correlated electron systems, such again as exotic magnets, heavy fermion compounds, and also high temperature superconductors. Strongly correlated electron systems. So, this is basically the structure of this course. Typically, I give this course with a blackboard. However, at the end of each chapter, I'm going to present a slide summary. Of course, these slides will be available to you. And in this slide summary, I'm also going to touch the basis of experimental way to detect properties of the many body systems, such as neutron experiments. We discussed experiment also in the setup of ultra-cold gases, namely Feshbach resonance, some necessary tools for detecting properties, tools to detect superconductivity, tools to detect superfluidity, and so on and so forth. So, again, we decide during the course how much emphasis we put to experimental tools, and we will see it during the course. Typically, in the normal life, we used to organize the guided tour to Electron. We have a synchrotron in Trieste and Basovitsa, and this is full-day guided tour. Typically, we do it at the end of spring, like in May. I hope that if the situation with COVID will improve, we will proceed with that, because the synchrotron is one of very important tools. You will learn from the first hand what and how was measured in the experimental labs of Electra, which is synchrotron in Trieste. Okay, I told you basically what we are going to discuss, and rather how we split and partition our course. But what is our main goal? Any questions related to the structure of the course and what is inside? Because it's very important to understand the logics of the course. And again, if you feel that you have some gaps in your education and you need to fill in this gap, we rather slow down. So it's not a goal to make very broad, discussion. If necessary, we can actually go deeper in each bullet of what I put on the blackboard. We have time for that. And again, let me say all this about physics. So I will speak very little about modern methods of many-body theory, which is quantum field theory, Feynman diagrammatics, then elements of topology and mathematics, appropriate mathematics to discuss modern topological system. All this deserves separate course. However, if you feel that you need another course which would be called methods of many-body theory, you are very welcome to raise this question. There was experience in the past that we met, actually, request of students and organized some additional lectures about modern methods of analytical methods of solid-state theory. Of course, you will have some other courses, and all what is going to be discussed here is, of course, in connection with other courses you are going to have during your stay in Trieste. And of course, you will learn modern numerical methods to deal with many-body theory, such as exact diagonalization, quantum Monte Carlo, DMRG, DMFT, and so on and so forth. The course which I'm going to teach is mostly going to be about physics. Therefore, you may think that this is a bit old-fashioned. Actually, it is not, since in each and every chapter I'm going to discuss quite modern developments of the modern many-body theory. But we need to find the optimum. Therefore, you need to learn some physics and also be introduced on how people deal with many-body theory. So what is actually many-body theory? What is actually many-body theory? I would say that first of all, we are going to deal with very, very large system consisting of yes.
Do we have any reference we can use?
Sorry?
Do we have any reference book?
Yeah, I'm coming to that. Sorry, I wait, just wait. So, before I start with the real topic of this lecture, which again I'm saying that we have today some introduction, namely we need to discuss all rules of the games, namely the structure of the course, what the course is about, how we organize this course, namely homework, exam, midterm exam, and then the last part of this introductory part will be literature, and then I come to discussion of symmetry, which stays. However, please feel free to interrupt me anytime if you don't understand what I'm saying, or if you have any question. Okay? So, we are going to deal with a very large system. Of course, one cannot solve such system numerically, even having big supercomputers. It's really a huge number of degrees of freedom. Therefore, we need to discuss some methods how to address questions about cooperative phenomena. So, namely, how to deal with the cooperative phenomena like body-state condensation, superfluidity, superconductivity, magnetism, which are the quantum phenomena. So, what is important? I'm saying it's cooperative. Most of the phenomena will be quantum. We need to address effects of interaction. And sometimes effects of disorder. What I mean by disorder is solid state with impurity, with some imperfectness, dislocations, disclinations, and so on and so forth. So, in order to do it, we need to actually develop some general approach and tools to description of this system. And this is what this course is about. And last but not least, what I forgot to mention is that sometimes these systems are in, sometimes out of equilibrium. This is probably the only course which you are going to have during the stage, which is going to address the kinetic phenomena, namely what happens with systems which are out of thermodynamic equilibrium. And we do it when we discuss the quantum transport, namely at the end of superconductivity and magnetism chapters. Again, if time permits, I can also give one or two lectures about so-called nanostructures, this modern technology, and progress in this modern technology, modern quantum technology, which is in the core of hardware of quantum computing. Again, quantum computing is itself very interesting topic, and one of the goals of this course is also to introduce you to what is going on nowadays. Not what happened, say, 20, 30, 50 years ago, but what are the most interesting problems which people working in the field of condensed metaphysics face now. Good. Yeah? Please speak louder. Impurities? Well, suppose you have a crystal and you have, so to say, foreign atom inside. Suppose you have a gold, for example, metal, noble metal, and you put some magnetic atoms like iron or chromium inside. There is very interesting physics appearing. Even the concentration of this magnetic impurity in non-magnetic atoms, in non-magnetic metals, is very small. And most of the existing systems, moreover, most of the interesting systems, like high temperature superconductors, are not stoichiometric. Namely, they have addition of atoms which people say they are doped by atom. So, for example, lanthanum-2 copper or 4. This is the first high temperature superconductor discovered by the North and Müller. Typically, in this stoichiometric configuration, it doesn't superconduct. Actually, it is insulator and antiferromagnet. However, if you dope it with oxygen, so you add small concentration of oxygen, at some critical concentration it starts to become a superconductor, and moreover there is optimal doping, optimal concentration of oxygen, which then leads to highest possible temperature of the superconductor transition. This is what I'm saying as effects of disorder and impurities. We come to this later. Lian, I don't understand what you are saying.
Hi, Professor. I think she was asking about the meaning of cooperatives, which you pointed out in the word cooperative.
Okay. Cooperative synonymous is collective phenomena. So this is a phenomenon which appears in the whole many-body system. The example of this cooperative and collective phenomena is Bose-Einstein condensation. The first example. We will see that this condensation is a property of bosonic system without interaction. And this is cooperative phenomena because Bose-Einstein condensation is condensation, so to say, in the moment of space. You will have a macroscopic number of particles occupying the lowest energy state corresponding to the zero momentum. So this is one cooperative phenomenon. Another cooperative phenomenon is a superfluidity. This phenomenon occurs in the weakly interacting Bose gas, which as a result of interaction between atoms acquires very interesting phenomena, namely this gas or this liquid can flow through capillaries without friction. This is why it is called superfluidity. This is another example of cooperative phenomena. The third example of cooperative and collective phenomena is a superconductivity. We will see that electrons subject to electron-phonon interaction form pairs, and these pairs, which are charged by the way, can conduct electric current without energy losses. So the system is characterized by zero resistance, zero resistivity, and therefore the electric current proliferates along the system without energy loss. This is yet another example of cooperative or collective phenomena. And we will see also that magnetism, which is the quantum property of solids, is also cooperative phenomena. Most of these phenomena are described in terms of the second order phase transition theory. So this cooperative phenomena is the phase transitions. Sometimes this is first order, sometimes it's second order. So we need therefore to learn how people deal with this cooperative phenomena, and phase transitions is one of the very powerful tools to describe this collective or cooperative phenomenon. Okay? Did I answer?
Yes, Professor, but I'm sorry to just bring you back a little bit. You were discussing something about impurities, about the lanthanum copper oxide, and you said something about if they put some impurities of salt or something.
Well, as I said, you have a crystal. Actually, these high temperature superconductors, almost all existing high temperature superconductors are very bad metals. So when you create a crystal which is described by this chemical formula, you will see that when you prepare a system precisely according to this stoichiometric chemical content, this system is insulator. So it doesn't conduct current at all. However, when you start to put additional oxygen into this system. So you create in your, so this is copper atoms. Then you put, so this is copper, you put oxygen, so this is oxygen, this is oxygen, and this is oxygen. Which is in between. But then, if you remove some oxygen, or you add some oxygen, actually here it's minus delta. You remove some oxygen, for example, you remove this. Then you create a possibility for electrons to hop. Therefore, the system in the presence of vacancies start to conduct current. We will see what are existing theory of superconductivity, and in particular, this model will be captured by so-called Hubbard model, two-dimensional lattice. I'm going to introduce you to some modern models to describe modern solid states. And as I said, in the presence of these vacancies, oxygen vacancies, system not only start to conduct current, but below certain temperature, it becomes a superconductor with relatively high temperature of superconducting transition. For example, in this first superconductor, by the way, it can also be doped with strontium. The temperature is about 35 Kelvin. It's still below the temperature of liquid nitrogen. However, it was a huge progress in development of new materials. And pretty soon after discovery of first high temperature superconductor, people discovered another system which possessed the same property, namely it contains a copper oxide plane, and it was yttrium, barium, copper oxide with a critical temperature of 91 Kelvin, which is above the temperature of liquid nitrogen, and therefore the era of high temperature superconductivity starts. We will discuss it in more details, but impurity means you create some vacancies in your system. Okay? So, did I forgot anything? Yeah. Now I would like to mention about prerequisites. So you see that this solid state theory is actually a combination of your knowledge which you already got from different courses. So since we are going to discuss mostly quantum phenomena, I will rely on your knowledge of quantum mechanics. Namely, Schrödinger equation, Heisenberg equation, equation of motion to describe single particle quantum mechanics, method of second quantization, and I hope that all this you already had in your course of advanced quantum mechanics. Did you do? Spinors, second quantization, wave function, Schrödinger equation, Heisenberg equation. In the discussion of magnetism of free electrons, namely Landau magnetism, diamagnetism, I will need your knowledge of quantum harmonic oscillator. Did you discuss quantum harmonic oscillator in details?
Yes.
So, you can tell me what is the level of degeneracy, what are Landau levels, or you just discuss it from the point of view of quantum mechanics. Do you know what Landau levels are? Because the same discussion we will need in order to discuss integer quantum Hall. For example, if we dwell into this business, I will adjust to you. It depends on you how fast, how deep, how slow we are going to be. And if you know everything, I would like to minimize, repetition is always good. Repeating things, especially if different people present maybe the same material, is still good because you can learn things deeper. However, if you feel that I'm talking only things which you already know perfectly, I will immediately switch to things which I believe you don't know. This depends on you. I'm ready to readjust my course to your level to accept the information and your level of education. Okay, I talked about prerequisites, and I already said that quantum mechanics is one of the most important prerequisites. The second important prerequisite is statistical mechanics. Namely, I need your basic knowledge of thermodynamics, of grand canonical ensemble, Gibbs distribution, partition function, and this I already start to refer during the first lecture. Do you already have it in your lectures on statistical mechanics? Including quantum gases, fermions, bosons, Fermi distribution function, Bose distribution function. I'm going to refresh it quickly today because this is introductory lecture. But I assume that you have it. My understanding that you didn't have tutorials in your course of statistical mechanics, right? Did you?
Yes, we did.
So, maybe we need to actually repeat something on more interactive level in order to make your knowledge broader and at the same time deeper. Okay, and then many-body system, quantum mechanics, statistical mechanics, and then of course I will need some calculational tools. In particular, linear algebra. This is what we need all the time: diagonalizing Hamiltonian, diagonalizing matrix, then ordinary differential equations, Fourier transform, sometimes calculation integrals in a complex plane. This is all what you need. Not all, but not everything. But this is definitely what you need to know, otherwise I will not be able to proceed. Of course, I will be presenting calculations on the blackboard. However, if you have a problem with understanding of what I'm doing mathematically, you need to tell me immediately, because then we will need to go back and rediscuss some calculus and mathematical tools. Okay. So far, so good. Now, literature. As I said, this course is combination of different knowledges. So therefore, there is no unique book which I'm going to use. And I'm not following any book in this course. However, I would like to recommend you some books which are definitely important for understanding. Since I already mentioned prerequisites of quantum mechanics and statistical mechanics, I will be referring to Landau-Lifshitz course of theoretical physics, namely volume 3 is quantum mechanics, volume 5 is statistical mechanics, volume 9 is, I would call it, advanced statistical mechanics, because in the classification of Landau, this is statistical mechanics part 1, this is a statistical mechanics part 2. Then there is, all these books are available in the library. Then there is a book of Abrikosov. He's a Nobel Prize winner. He unfortunately passed away a few years ago, which is called Fundamentals of Metal Theory. You should not be scared by the word metal theory. We are not going to deal with metallurgy. Metal theory means it's a Fermi liquid, superconductivity, and magnetism. And this is very deep and very brilliant book about modern approach to description of the metals. Then, for chapter of superconductivity, there was a book of Schrieffer. Schrieffer is one of the authors of Bardeen-Cooper-Schrieffer theory. He is also Nobel Prize winner. This book actually is small. It's about 200 pages. It is called Theory of Superconductivity. And for magnetism, it's a book of White, which is called Quantum Theory of Magnetism. Okay, and of course there are textbooks of the solid state physics. You can take any favorite. For example, for American systems they use Ashcraft-Mermin, 2-volume book of solid state physics. There is a popular course of Zeiman, Theory of Solids. There is a popular course of Kittel, Quantum Theory of Solids. You can take any of this book, whatever you like. Good. And the structure of what is the timeline. Typically I give a homework in the middle of course. Because in order to be able to solve this homework, you need to accumulate some knowledge. And typically I don't plan midterm exam. But this year we probably behave differently. I would probably prepare some midterm exam after we learn at least 2 chapters with very simple problems. And after this midterm exam, I will give a homework, which then I will collect at the very end of the course, and then we have a final exam. Again, everything depends on the situation with the COVID. So in 2020, I had an oral exam because we were in a deep lockdown, and there was no way even to come to ICTP. However, this year and at the end of last year, the situation improved a little bit, so we have chance either to have a written exam like we did it for all other courses, statistical mechanics, advanced quantum mechanics, which you're going to have tomorrow, and mathematical techniques and electrons and photons. So it will be a written exam. We will see, actually. I don't yet have plans for that. And of course, I'm going to plan some tutorials, and I would prefer and appreciate if we do it in the interactive manner. You tell me what are the difficulties, because typically, for example, I don't plan to discuss thermodynamics of ideal Fermi and Bose gases. I presume that you had it in the course of statistical mechanics. Did you? So, we will concentrate on something else. However, if you feel that you forgot or you didn't learn enough how to compute specific heat of metals and get linear in temperature low, and in particular show that it's proportional to the density of states, and so on and so forth. By the way, did you already have a notion of density of states? Okay, we will see what kind of tutorials you need when we start. Any questions about that? Also, I presume that you are not kids. You are students who already got master or bachelor degree, so you are ready to become physicists. Therefore, during each lecture, I will formulate some problem for you. And this is your attitude, your responsibility. You can start solving this problem, you can approach to me showing what you did, but I'm not going to force you. I will just indicate interesting problem. For example, I give you one at the end of this lecture, and then it is up to you whether to try to solve it, or completely ignore. I'm not going to force you doing anything, because you are students who learn at ICTP and who are ready to enter PhD program and proceed with your career as theoretical physicist. Good. Okay. Now I erased everything except title. And let's go quickly through the material which I'm going to refresh today, assuming that what I'm saying to you today, you already know. So this is a quick refreshment, but several very important concepts and several very important ideas. Let's start with symmetry. We are dealing with the quantum systems. And in quantum systems, the most important thing that particles, when I'm saying particles, are atoms, electrons, protons, neutrons, photons, phonons, whatever. I'm coming soon to the concept of quasi-particles and particles, but whatever I'm saying are indistinguishable. Namely, contrast to classical system, where you can label each and every item, in quantum mechanics, your particles are indistinguishable. Therefore, identical and indistinguishable. Let's start with a discussion of two non-interacting, indistinguishable quantum particles, zero temperature, quantum mechanics, sorry, this shock. Two identical, indistinguishable particles. So although, as I said, we cannot label them, I still put 1 and 2. And although this system should not know what is 1 and what is 2, and we will characterize the system of two identical, indistinguishable quantum mechanical particles by the set of coordinate, spin, if we need, which actually are arguments of the wave function. So the square modulus of the wave function gives you the probability density. And the wave function is subject of stationary Schrödinger equation. Okay. No interaction, nothing. Let's take sort of mental experiment. Let's interchange these two particles mentally. So I'm saying now this is 2 and this is 1. What changes? We have the same wave function, psi 2, psi 1. But since these particles are indistinguishable, the probability density should not fill this. Therefore, we can write down that the wave function after our mental experiment of exchanging two particles related to the wave function of the system before interchange by the phase factor. Because if it is so, then we square modulus of the wave function, and as a result, we have the same, either we interchange or we don't interchange. Let's take the second mental experiment and interchange these particles again. So this is 1, this is 2. With the same level of argument, we have a wave function psi 1, psi 2, which is related by the same phase factor by the function to the function psi 2, psi 1. And as I said, psi 1 and psi 2 is coordinate plus spin if necessary. And therefore, If we continue this line, this is e to the power 2I alpha, psi, psi1, psi2. If we look at the beginning of this equation and at the end of this equation, we immediately see that 2I alpha is equal to 1. So we got this equation only from the condition that our two quantum mechanical particles are identical and indistinguishable. Now we know how to solve this equation. This equation has two types of solution. First solution, if alpha is equal to 0, 2 pi, 4 pi, and so on and so forth. If it is so, this is equation 1, this is equation 2. From equation 1, we get that psi2, psi1 is equal to plus psi1, psi2. So our wave function is symmetric with respect to interchange the arguments. The second type of solution is if alpha is equal to pi, 3 pi, 5 pi, and so on and so forth. In that situation, we have psi2, psi1 is equal to minus psi1, psi2. And the wave function is antisymmetric. So this is sim, this is asim. Again, just from the point of view of indistinguishable particles, we get two classes of solution, symmetric and antisymmetric. And the system of main non-interacting particles, free particles, characterized by symmetric wave function, will be called bosons. And I will put index B here. And system characterized by antisymmetric wave function will be called fermions. As the next step, we will construct explicitly the wave function of non-interacting many-body bosonic and fermionic system, and use your knowledge of quantum statistics and derive distribution functions for fermions and bosons, which is Fermi-Dirac distribution function and Bose-Dirac distribution function. This is what I'm going to do during today's lecture. But you see, with a very general arguments of symmetry, we already arrived to very important conclusion. So, now, suppose we have a Schrödinger equation for single particle. I will call the single particle function is E phi. And we will have all states, quantum states for single particle, which we will numerate P1, P2, P3, and so on and so forth. Suppose now we have two bosonic particles, and we need to create bosonic function psi1, psi2 in terms of single particle wave function, and guarantee that this is going to be symmetric. So therefore we write phi p1 psi1, phi p2 psi2. I remind you that psi is coordinate plus spin if necessary, plus phi p1 psi2, phi p2 psi1. And in order to have it properly normalized, we put 1 over square root of 2. So you see that this wave function explicitly satisfies the law that it is equal to plus psi bosonic, psi2, psi1. So this state, P1, P2, P3, and so on and so forth, coming from the classification of solution of single particle Schrödinger equation, can be different or can be the same. Is it clear? Now we do the same for fermions. We assume that there are two fermionic fermions, and we need to construct the two-particle wave function of non-interacting fermions out of the wave function single-particle wave function. And in order to do it, of course, we can write phi p1 psi1, phi p2 psi2, but now we need to guarantee that this function is antisymmetric. Therefore, we put minus phi p1 psi2, phi p2 psi1. And again, we put 1 over square root of 2, normalizing factor. And here you explicitly see that this is minus psi fermionic psi2 psi1, right? You can check it explicitly. Question? Martha, I cannot hear you. Okay, but you also recognize that what you write down here is a determinant. Phi pi1 psi1, phi pi1 psi2, phi pi2 psi1, phi pi2 psi2. So how this determinant is called? This is the Slater determinant. You see that what I have written here is precisely this thing. So this is a Slater determinant. And we immediately arrive at very important property. Namely, if we assume that P1 is equal to P2 equal to P, then we have two rows which are identical, and if we have two rows of determinant identical, this determinant is equal to 0. Therefore, we come to very important property of fermionic system, which is known as a Pauli principle, which says that two fermions characterized by the very same set of quantum numbers should not appear. So there exist no states with the two fermions occupying the very same quantum state characterized by the very same quantum numbers. Therefore, if you have some quantum state denoted by index p, there can be only 0 fermions in this state or 1 fermion. For bosons, we don't have this property at all, because we can easily imagine the situation where two bosons occupy the very same state. Okay? You see, here, starting from the symmetry arguments, we arrived to very important property of quantum many-particle non-interacting states, which discriminate between bosons characterized by symmetric wave functions and fermions characterized by antisymmetric wave functions. Now, if we want to construct the many-body state for non-interacting fermions and bosons, what shall we do? So now we have not 2 particles but n particles. Okay, for bosons, we have a wave function characterized by psi1, psi2, psi-n. What we need to do, we need to take a sum of all permutations, phi p1 psi1 times phi p2 psi2 times phi pn psi-n. Then we should normalize properly, and the normalization factor n1 factorial, n2 factorial, and so on and so forth, divided by n factorial, square root, where n1, n2, n3, and 4 tells us how many particles are in the state with the P1, P2, P3, and so on and so forth. And of course, condition that sum over n, sum of I and I, is equal to the total number of particles. So we prepared, we constructed the many-body wave function of non-interacting bosons such a way that we took a product of single particle wave function and symmetrized it over all permutations of indexes P. Okay, you can explicitly check that this function is symmetric with respect to any interchange of any arguments. I see the chat. Sorry, I cannot do many things. Maybe open the chat too. Actually, sound seems to be not good, and the left is a bit dark. Okay, I will collect all these inputs at the end of the session. I will copy it and report it to computer section, but in order to improve the second lecture. However, I cannot change, I'm not a computer guru, and moreover, I don't have access to the system. I apologize for that. Okay, now how we construct the wave function of n non-interacting fermions. We already know the answer, namely we need to construct the determinant. So psi fermionic psi1, psi2, psi n is a determinant. Phi pi1, psi1, phi pi1, psi2, phi pi1, psi n, phi pi2, psi1, phi pi2, psi2, phi pi2, psi n, and we have a phi n psi1, we have an n by n determinant, phi n psi n. So this is a Slater determinant which is describing the system of n non-interacting fermions. And again, if we take two quantum numbers, P1 and P2 being the same, we immediately get that determinant is equal to 0. Therefore, Pauli principle works. Okay? So far so good. Now, what did we learn? We learned the following, that there are two systems, two kinds of wave function describing of many-body non-interacting system. So one type of function is fully symmetric, this is bosons, and another type of wave function is fully antisymmetric, this is fermions. For bosons, arbitrary number of particles can occupy given quantum state characterized by given set of quantum numbers. Therefore, the occupation of given quantum state can be 0, 1, 2, 3, 4, and so on and so forth. For fermions, it's completely different. Due to Pauli principle and structure of Slater determinant, we can only have two possibilities. Namely, we can have either 0 fermions occupying given quantum state, or we have 1 fermion occupying this state. 2 fermions is impossible. 3, 4, so on and so forth. Okay, how can we utilize this knowledge? Well, I will end up today's lecture by computing the fermion-Bose distribution function. However, before I do that, let me give two important remarks. First of all, there is a connection between spin and statistics. And this connection goes far beyond the scope of my course. It is Pauli theorem, which people study in the course of relativistic quantum mechanics. And this theorem says that particles characterized by integer spin, 0, 1, 2, 3, 4, 4, 5, are bosons, and particles characterized by half integer spin, 1 half, 3 half, 5 half, are fermions. This is a connection between spin and statistics. And second comment is, what are examples? What kind of examples we know of different types of particles? So if we are talking about elementary particles, electrons protons, neutrons, neutrinos are fermions. Electrons, protons, neutrons are characterized by spin 1/2, neutrino is spin 3/2. Well, then elementary particles like photons are bosons. So photon has a polarization which is spin 1. But in the course of many body physics, we will be seldom dealing with the particles, because we are dealing with the collective and cooperative phenomena. In order to describe this collective and cooperative phenomena, we need to describe low-lyzed excitations, or the same as quasi-particles. So excitations and quasi-particles are synonymous. So by diagonalizing your Hamiltonian of interacting system, we will get the ground state energy and we will get excitations above the ground state. This is what we did, for example, in the course of electrons and photons. And then you arrived to the situation when vibration of atoms in the lattice create some collective excitations of quasi-particles, which are phonons. So phonons are bosons. Spin of phonon is 0, so these are quasi-particles with which subject of Bose statistics, which we are going to discuss right away, and which are characterized by symmetric wave function. In addition to bosons, we can refer to magnons. This is what we are going to discuss in the course of magnetism. These are excitations, magnetic excitations, associated, for example, with a spin flip. So the magnons are quasi-particles or excitations with spin 1, as we will see. Then we can talk about excitons. Excitons are bound state of electron, positive, negatively charged quasi-particle and hole. We will see it in the Fermi liquid. So this exciton is a composite particle. Therefore, it can be either in singlet state or in a triplet state. Therefore, its spin of exciton can be either 0 or 1. Again, these are quasi-particles subject to Bose-Einstein statistics. And if we need examples of quasi-particles which are subject of Fermi, which are fermions, we will be dealing with it in the course of Fermi liquid theory. These are elementary excitations in metals, which are called electrons. Please don't confuse it with the name of elementary particle. It has the same name and force. We will come to this discussion the day after tomorrow on the second lecture about ideal Fermi gas. Okay, and now let's conclude bringing the knowledge from quantum mechanics, namely the symmetry argument, which allows us to construct the wave function, to statistical mechanics. Okay? So let's start with bosons. But before I give two examples, let's have a convention. So we will be dealing with a box. So we are dealing with non-interacting particles or quasi-particles. So this is a box by the size L. We can solve our non-interacting Schrödinger equation in the box. And in the box, typically we apply to the Schrödinger equation periodic boundary condition. So box, in a sense, is a sort of torus. These are periodic in all coordinate boundary condition for solution of the Schrödinger equation h psi is equal to h psi. Sometimes, contrast to the box model, I will be dealing with a quantum well model with infinite walls. The difference between box and infinite wall, of course, one can imagine multidimensional quantum well, is that inside the wall you don't have interaction, but the boundary condition for solution of quantum mechanical problem, which we need to find Q1, is that you have your wave function equal to 0 at the wall's position. Again, this is 0, this is 1. This is the difference between box model and well model. But whatever we do, we can write down that the energy of free particles is characterized by the wave vector. So sometimes for fermions we need to, for bosons, from now on I will consider bosons characterized by zero spin. So whenever I talk about bosons, forget about spin. For fermions we cannot do that. For fermions we have additional quantum number, which is spin, plus, and projection of the spin to the quantization axis is either 1/2 or -1/2, but only for fermions. So this is quasi-momentum. So far I'm not going to consider electrons in the presence of periodic potential. This is what you did in the state of, in the course of electrons and phonons. What I need is the quasi-momentum K, which is going to characterize the quantum state. So I'm going to consider partition function, which is sum over nk e to the power mu minus ek over kbt to the power nk. So nk are occupation number, which I remind you for bosons are n, 0, 1, 2, 3. Then thermodynamic potential omega is k, is minus kbt logarithm zk, and for full thermodynamic potential omega we need to sum over all k. These are basically basic formulas which I need to refresh you. So what is what here? Mu is chemical potential, T is temperature, omega is thermodynamic potential, Zk is a partition function. From now on, I will adopt the system of units where Kb, which is here, is a Boltzmann constant, is equal to h bar, is equal to 1. Therefore, I will drop h, I will drop Boltzmann temperature, therefore I will measure temperature and energy in the very same unit. Saying that the Planck constant is equal to 1 in the system of units which I am going to adopt means that the temperature, energy, and the frequency are measured in the very same units. Okay? Okay, so now we do the calculations. And this is very simple. Bosons. We first calculate Zk. Zk is when the occupation number nk is equal to 0, we have 1. Plus, if nk is equal to 1, again we conclude partition function characterized by the index staying for the state k. This is my former indexes p1, p2, and p3. This is what I did. So, e to the power mu minus epsilon k over temperature plus e to the power mu minus ek over temperature squared plus and so on and so forth. So, what we see here is a geometric progression. And geometric progression converges if e to the power mu minus epsilon k over temperature is smaller than 1. Which means that mu minus epsilon k is negative But since epsilon k, energy of free particle, k square over 2m, is always positive, we conclude that the chemical potential of bosonic system should be negative. If it is so, then Zk is equal to 1 divided by 1 minus e to the power mu minus ek over temperature. Then omega k is equal to minus t logarithm Zk, or it is equal plus t logarithm 1 minus e to the power mu minus epsilon k over temperature. Okay? So this is bosons. Now we need to do the last step, namely the distribution function and bosons with a state k is equal to minus d omega over d mu. So we need to take a derivative of this function. Let's do it. So we have plus t, 1 minus exponent, mu minus epsilon k over temperature. Now we have minus e to the power, plus and plus also minus here, mu minus epsilon k over temperature, and times 1 over temperature. So we come to the Boson distribution function, which characterize the average occupation number characterized by the index k, which is 1 divided by e to the power ek minus mu over temperature minus 1. Okay? Okay, let's repeat the same calculations for Fermi. So, Zk for fermions, this is bosons. These are bosons. When we take a summation, if nk is equal to 0, we have 1. If nk is equal to 1, we have e to the power mu minus epsilon k over temperature. But from the Pauli principle, we know that the given quantum state characterized by the quantum number k can only be occupied by 0 or 1 electron. I do this calculation per projection sigma. So this is Ek sigma. I assume no magnetic field, therefore the state with energy k spin up and stay with the momentum k spin down are degenerate. And this is correct in accordance with the Pauli principle, because projection to the spin is a discrete quantum number which is different. So the same energy level characterized by quasi-momentum k can be occupied by 2 electrons characterized by 2 different projections of a spin. So, and that's all. I don't have terms in my partition function anymore. Therefore, omega kf is equal to minus t log 1 plus e to the power mu minus epsilon k over temperature. And n fermion bar k is equal to minus d omega k boson omega k fermion over d mu is equal to plus 1 temperature 1 plus e to the power mu minus epsilon k over temperature, e to the power mu minus epsilon k over temperature, 1 over temperature. So, what we have here is the Fermi distribution function and Fk, which is 1 divided by e to the power Ek minus mu over temperature plus 1. Last comment before I finish. Let's take limit both for Fermi and Bose statistics that Nk average is much smaller than 1. Which means that e to the power mu minus epsilon k over temperature is much smaller than 1. I remind you that for bosons, for example, chemical potential is negative or non-positive. For fermions, it's large and positive. But if we assume this condition, what we will get that for Bose distribution function, Nk Bose average is approximately equal e to the power mu minus Ek over temperature, which is a e to the power minus Ek over temperature. This is what you recognize as a Boltzmann distribution function. And for fermions, we have pretty the same. This is e to the power mu minus epsilon k over temperature, which is a e to the power minus epsilon k over temperature, where a is equal e to the power mu over temperature. For fermions, for bosons, as I said, mu is negative, and this condition is already satisfied. For fermions, in order to satisfied for, say, temperatures larger than temperature of Bose and condensation, which we are going to discuss later. For fermions, this condition is satisfied in the classical limit, where the chemical potential also becomes negative. Chemical potential, as you remember, also depends on temperature. This is one of the thermodynamic potential. So what we learn from here, that if this condition is satisfied, our two cases of quantum statistics associated with the Bose-Einstein distribution function or Fermi-Liouville distribution function and with the Boltzmann distribution function. So Boltzmann statistics is limiting for both quantum case, fermions and bosons. Okay, and now, as I promised, the problem. The problem is about so-called Gentili statistics. Let's introduce more general principle, exclusion principle. So Pauli principle is exclusion principle because it says that fermions can occupy given quantum state with a occupation number either 0 or 1. Let's assume that given quantum state can be occupied with the occupation number 0, 1, 2, 3 up to certain number m, and that's it. So if we assume that, what kind of statistics we get at the end of the day? This statistics is known as Gentili statistics, and this is the problem which I would like to give you to think about. Derive distribution function using general exclusion principle, which is different from fermionic Pauli principle and bosonic, where you don't have exclusion, just limit the number of states occupy number of particles occupying a given quantum state by some number of m, and see whether this distribution function closer to fermions or closer to bosons. Okay, that's all for today. Any questions?
What's the name of the
Gentili. I'm not sure that I spelled it fully correctly. Gentili statistics. And this is what I said. Nk Gentili is equal to 0, 1, 2, m, and that's it. Okay, more questions? So, If you don't have more questions, before I quit this session, I copy the chart and send it to the ICTS, and we meet on Wednesday this week. Okay, thank you.